All right, guys. The This is the final video. I think it's going to be well. I say that it may turn out that I have to split this video into two parts so I can upload it. But this is going to be a long video. This is the second part of the exam study guide for the final. What I want to do, what I've done is I've uploaded this worksheet to Blackboard. But just in case you don't have a printer, I'm not going to keep this up like I do in some of the other videos. I'm going to have just a clean sheet of paper, white sheet of paper, and I'm going to work the problems for you. I will tell you, I don't think that in the version that I uploaded to Blackboard, I don't think these sample sizes were provided, so make sure you make that note, make that addition. And what I'm going to do is I'm going to go through each page of this, so if you don't have the resources to print out a copy of the handout, you can take a screenshot and just keep it handy. So, guys, there's the first page that we're going to go over. You can see we've got a lot going on. Here's the second page. So pause that and take a screenshot if you will. If you don't have resources to print out. And I picked up two pieces of paper here, which wasn't the intent. And there is the third page. All right, so we got 12 problems. Some have multiple parts. So we're going to go through these and work every one. It's going to be excellent preparation for you to get ready for the final exam. All right. So problem number one is something that you're definitely going to encounter. So it says draw the rejection region for the hypothesis test for the population mean or proportion. Give the appropriate conclusion. So we want a couple things here. We want the for all these, we want the rejection region, and we want the appropriate conclusion. Now, notice here that we're using something different than the p-value approach. So note we are not using the typical p-value approach. But that's okay. I mean, this is just a different way of doing problems, and we encounter these sometimes. So, guys, for the first one, here's what we got. We are testing H sub O mu equal 195, and H sub A mu not equal to 195. So this tells me that I have a two-tail test. Okay, and my test statistic is negative 2.11, and my alpha level is 0.05 with a sample size of 50. So what we want to do is we want to find in the t distribution, degrees of freedom equal 49. We want to find the negative t star and the positive t star that separates the reject region in each tail with the fail to reject. Well, guys, we have to go to our alpha here, and our alpha defines the proportion under. Well, it defines the percentage of the area under the curve that we give to the reject area. So this is saying that we have 5% of our area under this curve that we're giving to the reject. Since we got half of it here and half of it there, we have to put 2.5% or alpha over 2 in each tail. So I'm just going to focus on this one right here. So what I would do there is I'd use inverse t. And for this point right here, I need 0.025 to the left. And I have a degrees of freedom of 49. So that value is negative 2.01 over here. And because of symmetry, this is positive 2.01. So gang, that's my rejection region. So I can check that off. Now my appropriate conclusion is we have to find where our test statistic falls. Well, our test statistic falls somewhere to the left of negative 2.01. So negative 2.11, which is our test statistic, falls about there, which is in the reject region. So our appropriate conclusion is reject H sub O. Second problem. H sub O mu less than or equal to 195. Mu greater than 195. Alpha 0.05. T is 1.07. Sample size 14. Guys, we don't have a two-tail test here. We got a one-tail test. And since we're doing greater than, we know our rejection region is going to be in the greater than portion. So up here we have our reject H sub O region. And everything to the left, hence less than or equal to, is our fail to reject. So we want to find the value there. Now our alpha is 0.05, and since we're not doing a two-tailed test, that means that we want 5% of our area right of this line. But we know from using inverse t a lot that we know we always have to use the area left of that line. So what I need again is I need inverse t. The area to the left is 0.95. I have a sample size of 14, so my degrees of freedom are going to be equal to 13. So that value, the line in the sand, is going to be 1.77. And again, this is our critical value. Our 1.07, now guys, remember, in the center of your distribution when it's been standardized is 0. Our 1.07 our test statistic falls there, which is to the left of the 1.77, which is the line in the sand between reject and fail to reject. So our critical region is everything to the left of 1.77 is our fail to reject. Everything to the right of 1.77 is our reject. Our 1.07 falls in the fail to reject. So our appropriate decision is fail to reject H sub O. 1C. Here we are testing a percentage because there's a P there. Versus less than or equal to less than 0.60. We're testing at 0.10. N is 200. And Z is negative 1.89. This number right here, even though we have it, is irrelevant. Because the sampling distribution for percentage problems doesn't rely on the t distribution. The t distribution relies on degrees of freedom. The z distribution has a normal distribution, mean zero, standard deviation 1. It doesn't rely on degrees of freedom, so it doesn't rely on your sample size. So what we need here is we have a left tail test because we're looking at less than. So gang, this is going to be the reject H sub O region. And this is going to be the fail to reject. Remember, our alpha value corresponds to the area in the reject region, either total or wholly. And this is wholly because there's no two-tail test. So I want to find the negative z star here. And again, remember, means 0 when we standardize something. For the z distribution, I want to find the z critical that has 10% of the distribution to the left of it with mean 0, standard deviation 1. Well, gang, instead of using inverse t, I use inverse norm. So I need 0.10 to the left of my line with a mean 0, standard deviation 1. And it's negative 1.28. Our test statistic is negative 1.89. Which falls right there. So our appropriate decision is reject the whole. Alrighty. Number 2. All right, number 2 says the mean and standard deviation alkalinity levels for 53 randomly selected lakes in Florida, 37.5 and 38.2. So the mean is the sample mean is 37.5. Sample standard deviation is 38.2, indicating to me that we have a severely positively skewed distribution. Use the sample data to see if there's evidence that the average alkalinity level in Florida lakes is greater than 35 milligrams. I assume that's per liter. So part A, what is the population under study? It's the alkalinity levels of the lakes, well, actually 4. The lakes in Florida. Does this study pertain to a quantitative or categorical data? Clearly quantitative, because the mean has been reported. The average. What is the value for the sample mean? That's the value that you get from the 53 selected lakes. There are 2 means reported in this level, or in this problem, 37.5 and the 35. What's the difference? Well, this is our sample mean. This is the population mean statement. Somebody thinks that they're drawing this line at 35 as a statement for the entire population. They think, or at least they'd like to test, that the alkalinity level is higher than this. So you think about this as a statement for all lakes, and someone wants to test that the alkalinity level is higher than 35. Report the appropriate hypotheses. Where do we always start? What we want to test in the alternative hypothesis. We want to test that the mean is greater than 35. Therefore, we know that the mean and the 35 have to be part of this statement, and it has to be the opposite mathematical inequality. calculate the test statistic and p-value. Guys, anytime I can use my calculator to make this kind of statement, to make this kind of, take this kind of test, I'm going to do so. Now, we know from reading the problem that sigma is not given. So we know we're going to use a t-test. So we know that our test statistic is going to be a t-value. And of course, we're going to end up with a p-value. Well, gang, I'm going to do that with my calculator. So I'm going to go to stat, I'm going to go over to test, and I'm going to conduct a t-test. I don't have the 53 numbers, I have the results. So the mean that we're testing here is 35. My sample mean is 37.5. My sample standard deviation is 38.2. My sample size is 53. And we want to test greater than. Now we can go to calculate. And we get our test statistic. Our test statistic is 0.48. And our p-value is 0.32. G. What is the appropriate decision? Our p-value, again, our alpha wasn't given in this problem. So anytime your alpha is not given, you have a default of the industry standard, which is 0.05. So part G, what's the appropriate decision? Well, our p-value is greater than our alpha, so we fail to reject. We can't reject that statement. So we must conclude that based on the sample data, that the mean alkalinity level in all the lakes in Florida is less than or equal to 35. So the person who suspected that the alkalinity level is greater than 35, their suspicion is not confirmed. Okay? Now, H, are the results statistically significant? Nope, they're not. Statistical significance happens when our p-value is less than alpha, when we get a reject. And then I calculate and interpret the 95% confidence interval. Guys, again, with your calculator, this is really easy to do. You've already done a t-test. Let's go grab the t-interval. Guys that knew you were coming, so it's imported everything in. So 26.97 up to 48.03. So there's a 0.95 probability that the alkalinity level for all the lakes in in Florida are somewhere between, say, 27 and 48. Notice it contains our 35. So our confirmation from the confidence interval, or I'm sorry, our results are confirmed from the confidence interval. Problem number 3. We have this confidence interval for a population percentage. And the confidence interval that we get here is 25.4%. And guys, again, this is a 95% confidence interval. Now, guys, remember these problems deal with the Z distribution. No degrees of freedom. Anytime you have a percentage problem, you don't have a T distribution. Anytime you have a percentage problem, whether it is a test of hypothesis or confidence interval, you model this with the z-distribution. No t-distribution will ever be involved in this class with a percentage problem. First of all, what's the margin of error? Guys, you should be really good at this by now. The margin of error is just plus or minus the big number minus the small number divided by 2. So we can, well, I can do that in my head. I don't know if you can or not. Just to confirm that my, yeah, okay. So plus or minus 2.55%. Now, typically in problems that deal with percentages, our line in the sand here, we like to have a margin of error of at least 3%. I'm sorry, at most 3%. Now, we want our margin of error to be 3% or lower. So seems to be a reasonable estimation of this unknown percentage that we're trying to estimate. Now, the next thing is, what is the sample size? We got to find something that brings together the two quantities of margin of error and sample size, because we know our margin of error up here, and we're desiring the sample size that created this. Well, guys, we have that. We know in these problems that the margin of error is the z-critical, the square root of p hat times 1 minus p hat over n. Now, you might be thinking, well, hold on, there's a major problem here. We don't know p hat. Oh, yeah, we do. Recall that the confidence interval formula is this nasty mess. What's that tell you? We take a value in the center, this p hat, and we add margin of error to create a right endpoint of the interval, and we subtract margin of error to create a left endpoint of the confidence interval. Guys, what resides smack dab in the center of our interval? The value that we got from our sample. We build this margin of error around because we understand there's nothing holy about this sample. It's one of infinitely many, so we want to allow room for error, margin of error. So guys, if we can find the value that sits smack dab between 25.4 and 30.5, then we have our p hat. Our p hat has to reside smack dab in the center of that interval. Well, guys, the easiest way to find the center of an interval, I mean, let's just think about it. What if you have an interval from 2 to 10? What's the easiest way to find the number in the center? Add the 2 and divide by 2. 6 is in the middle, right? If you take 6, 4 units to the bottom, 4 units to the top, it says that's in the center. So guys, the easiest way to find the center is to take the 2, add them together, divide by 2, not to be confused with the margin of error. The margin of error is trying to find the difference between the center and each endpoint. This is trying to find the value that's smack dab in the center. And you'll see when you do that, you get 27.95%, which is precisely p hat. So gang, we know that our margin of error was 2.55%. After all my screaming and yelling and everything, you should know by now. I'll tell you what, I'm going to start a new sheet of paper because we've got a lot going on here. You should know by now you never, ever, ever, ever use a percentage in arithmetic. So we're going to use 0.0255. We should know that the Z critical, guys, what I'm using right here is I'm using this right here. I'm just filling in the information that I know. I found p hat now. All I am missing in this entire relationship is n. So my margin of error that I got right here is 2.55%. So I'm using 0.0255 there. I know that the Z critical value for a 95% confidence interval is 1.96. I now know over here that my p hat is 0.2795. What's 1 minus 0.2795? Well, let's use our calculator. It's 0.7205. What's the sample size that created that? We got to solve for n. All right. First thing I'm going to do here is I'm going to take 0.0255 divided by 1.96, and then I'm going to realize that I've got everything over here. It should be reasonable that we square both sides. So on the left-hand side, I have 0.0255 over 1.96 squared. And on the right-hand side, I have 0.2795 times 0.7205 over n. Guys, remember this is all over 1, or can be thought that way. I've shown you a trick in previous videos where you can take the numerator and if you have a proportion, you can take the numerator and denominator, switch those. So on the left-hand side, I have n over 1. I'm not going to put the 1 there because that's redundant. So I have that. Can we put that in our calculator without doing something goofy? I think we can. So in the numerator, I need 0.2795 times 0.7205 divided by, I want to put this in parentheses because I have to square it all, 0.0255 divided by 1.96. You guys will need to square that. So we have 1189. Always round up. So our sample size is 1190. That's an involved problem. That's a tough problem. Takes a little bit of time, even if you're pretty good at this stuff. All right, gang, next problem is the National Center for Health Statistics reports that 74% of women have been married by the age of 30. I don't believe that report, but I'm not going to get into reasons I don't. A representative from a competing health organization feels that this percentage is too high, so they must think that it's too low. Or I'm sorry, they think it's too high, so they must think it's lower. To test the claim, she surveys a random sample of 125 women between the ages of 30 and 44 and finds that 91 of them were married at least once by the age of 30. Does this evidence support the representative's claim that less than 74% of women have been married by the age of 30? All right, gang, first, what's the population under study? Well, it's marriage status of American women up to the age of 30. And I guess technically you'd say from 18 to 30, although, I guess there are people that get married before they're an adult, which seems, yeah, it's their choice. B, does this study pertain to quantitative or categorical data? Well, when you look at all this and you see 74% and 30s and 91s and 125s and all these numbers, it's so tempting to say that it's quantitative. It's not. It's categorical because it deals with the percentage. Why is it categorical? Well, you either have been married by, well, if you're a woman up to the age of 30, now you either have been married or you have not. So the answer is either yes or no to this that's under investigation. All right, gang, p-hat is always the count out of the whole for your sample. So it looks like that 91 out of the 125 who were sampled had been married at least once. So you can leave it like that. I typically like to put this as a decimal. .728, but you don't have to. 91 over 125 is reasonable. It's the same thing as .728. All right. Part D, what percentage of the women who were sampled had been married? Well, 72.8%. It's a weird question, and I made that up. Report the appropriate hypothesis. Well, we're dealing with a percentage, so we use P. The representative would like to test less than 74%. So guys, we know that letter and that number have to be in the null as well. And we put the opposite inequality up there. 0.05, the alpha is not given. So again, if it's not given, the default is 0.05. Now, F, calculate the test statistic. Well, guys, we know the test statistic for these types of problems is Z star. And we know the p-value is just the p-value. All right, I'm going to use my calculator. All right, so I'm going to go stat, test. I should know by now that this is a one prop Z test. My dogs are losing their mind for some reason. Funny thing, they're leaving my dogs. All right, so P0 here is .74. My count is 91. The total sampled was 125 women. And I want to test less than. Calculate. You can see that your test statistic here is negative .31. And you can tell that your p-value right here is .38. If you prefer to just put .38, that is perfectly fine. All right, G, what is the appropriate decision? Our p-value is higher than our alpha. So we failed to reject H sub O. So our evidence is conclusive that the p is greater than or equal to .74. Our evidence is not conclusive that the percentage is less than .74. So this person who claims that less than 74% of American women have been married by the age of 30, our test results do not support his or her claim. Are the results statistically significant? Nope. To be statistically significant, your p-value has to be less than alpha. You have to reject the null. And then I calculate and interpret the 95% confidence interval. Guys, stat, we did a one prop Z test. You should know by now we would do a one prop Z interval. It's waiting on you. Knew you were coming. So we have, looks like 65% to 80.6%. 6%. So we can say that the 0.95 probability that between 65% and 80, essentially 81% of women have been married at least once by the age of 30. So quite a few. All right, number 5 says a 90% confidence interval was calculated for an unknown mean. So number 5, let's just write down the things that are important. So we have a 90% confidence interval, unknown mu. Makes sense. If mu was known, we wouldn't need to estimate it. Population standard deviation equals 5. Sample size was 35. What was the critical value? Well, guys, this is kind of gives you some information, and it turns out this is unneeded. When you have the population standard deviation given, then you know you're going to be using the z-distribution, which follows a normal distribution, mean 0, standard deviation 1. It's the t-distribution that relies on the degrees of freedom, which relies on the sample size. If this value wasn't known, then we would be using the t-distribution. But when this value is known, we use the z-distribution. So therefore, we need the z-critical for the 90% confidence interval. So guys, what do we do? Well, just like we've always done. Put the level in the middle. We ask ourselves, how much is missing? Put half of it here, put half of it here. So this value, which resides right there, is going to have 5% of the distribution to the left of it with mean 0, standard deviation 1. Sample size is irrelevant because the population standard deviation is known. So guys, correct answer, negative 1.645. Number 6. Very similar to number 5. 90% confidence interval. Mean is unknown. Again, makes sense. You're not going to estimate something that's known. Well, I'll tell you what. I made a mistake there. I copy and pasted and didn't edit. What I meant to say in number 6, that sigma is also unknown. So that should say a 90% confidence interval was calculated for an unknown mean and unknown with an unknown population standard deviation. If I don't change that, it's exactly the same problem we did in number 5. I wanted to point out to you that the problems can be set up kind of similar, but it all depends on whether or not the population standard deviation is known, depending on whether we use inverse norm or inverse t. So guys, change that. Sample size is 35, which is relevant in this. Find the critical value. Guys, this together says that we use the t-distribution. So our test statistic is going to be the t-critical. Now, one thing to keep in mind back here, we found this one, which was negative 1.645. I got a little sloppy here. That should be actually plus and minus, because this is going to be the negative 1.645. This is going to be the positive 1.645. So should include both of those. My bad. First mistake ever. So guys, what we got? We got the t-distribution. We got 90% in the center. How much is missing? Put half there, half there. But this uses the t-distribution, degrees of freedom, 34. So we're going to focus on this one right here first of all. So we're going to use inverse t, 0.05, comma 34. So that's negative 1.69. So we know that negative 1.69 is going to be this one. And we know that the positive of that is going to be over here. So the critical value for this confidence interval would be plus or minus 1.69. Guys, we're rolling right along. We're, I guess we're on page number 3. This might not take as long as what I thought. All right, number 7 is an interesting problem. This actually really did happen. In January 2009, 2 students made worldwide headlines by spinning a Belgium euro 250 times and got 140 heads. Well, if you think about this one longer than a second, you would think that if this is a fair euro, that you would get about half heads and half tails. So it would be reasonable to think you'd get 125 heads and 125 tails day in, day out. But we know that things don't work out that way. If I flip a coin 10 times, it doesn't necessarily mean I'm going to get 5 heads and 5 tails. But I would be very surprised if I got 9 heads and 1 tail, or even 8 tails and 2 heads. I would expect it to be about 50% heads and 50% tails, and it appears from this spinning, if the coin is fair, that I should have got something close to 0.5. So anyway, let's just play this out and see how it all happens. So what's the value for p hat? Well, they got 140 out of 250. So we can use our calculator to see that it was 56%. 56% of the time it landed on heads. Now, is that too high? Well, I don't know. I really don't. I don't even know until I work the problem. It seems like that we should get something closer to 50%. That seems a little high to me. But maybe it's not. Maybe just by chance we happen to get more heads on these 250 rolls. So I don't know. So let's play it out. To calculate and interpret the 95% confidence interval. So let's use our calculator and run that. This is a percentage problem, so you should know by now we use a 1 prop z interval for this. So we have 140 out of 250 at 0.95 level of probability, or 0.95 level of confidence. So we get 49.8% up to 62.1%. Now, what would indicate a fair coin? A fair coin to me would be that if I spun this euro, this Belgium euro, a million times, a zillion times, a trillion times, a quadzillion, however you want to put it, that 50% of the times it would land on head, 50% of the times it would land on tails. Well, this sample of 250, I didn't get that. But when I generalized to the entire population, notice that my interval contains 50%. So right now, I'm concluding it seems like to me it's a fair coin. Next thing was margin of error. Was my margin of error high enough? Big number minus small number divided by 2. I want something about 3%. and I get 6.15%. So I'll tell you right now, I am concerned with sample size. I need to tell these two brothers or two students or whatever they were that they didn't spend enough. I'd like to get this sample, this margin of error down to 3, but I don't have that luxury, so I've got to work with what I got. Part D, does the evidence indicate that the euro was not a fair coin? Well, that's what we're testing. Fair coin tells us that the percentage is not 0.50. We're testing that against percentage being 50. No reason to test other than 0.05, so I'm going to carry it out. Stat. I'm going to run a 1 prop Z test. So I've got 0.5, and I'm testing less than. Or I'm sorry, testing not equal to. A fair coin, the reason I don't put less than or greater than right there is fair could either be far too many heads or far too many tails. So either side, I have unfair. I'm going to calculate tunnel vision on the p-value. So my p-value is 0.058. Which is greater than my alpha. Fail to reject H sub O. Fail to reject H sub O says the most believable statement is your null hypothesis. P is 0.5, fair coin. It's close though. I tend to, I know is that if we doubled this, let's say we doubled it and the results stayed the same, we ran it 500 times, in 280, it'd still be 0.56, wouldn't it? Let's just do that. I think this is going to be worthwhile. If we did multiplied, we doubled our result. Now you don't know that's going to happen. You've got to sit there and just flip it another 250 times and see what happens. But let's just assume that the next 250 produced results like the first 250. So in this case, I would have 280 out of 500. 56%, right? So it kind of leads you to believe that the results would be the same because they wouldn't be. Let's see what happens here. Sample size is going to reduce my p-value. I still want the 0.5, but here I want to go 280. And I want to assume again, I doubled my sample size. Now I'll go calculate, I'm going to get a p-value less than 0.05. There's something called power in a test, and power is the probability that you reject a false null. Should have got into that more, but we didn't have time. So sample size does affect the p-value because sample size drastically affects your standard error. All right, number 8. Guys, we're rolling right along. This is still going to be kind of a long video, but not as long as I thought. All right, we are testing mu equal 195 versus mu not equal to 195. And we're testing at the 0.05 level. And we don't have any information as provided in this example, but we do know that the 95% confidence interval is 182.35 up to 192.65. What is the appropriate decision on the null hypothesis? Now, guys, one way of thinking about a confidence interval, and it's not exactly correct, but it's a decent way of thinking about it. This interval has about a 0.95 probability of containing mu. 95% of the time, this confidence interval that we produce from a random sample is going to get it right. So 0.95 is pretty good, right? There's apparently some claim that the mean of this population is 195. We have to think is 195 in our interval, and it's not. We have this mean value of 195, yet our entire confidence interval, which ranges from about 182 up to about 193, is below the claim. So what we can conclude is we should reject the null because our confidence interval, which is 0.95% of the time right, it's a horrible way to say it, but it's a decent way of thinking about it. There's a 0.95 probability that this interval contains mu. It's in there someplace. But the hypothesized value of mean isn't in there. So guys, I'm scratching that out. I don't believe mean is 195. I believe it's somewhere between 182 and 193. Since this entire interval is below 195, I feel comfortable saying statistically that I feel that the mean is less than 195 based on the confidence interval. Number 9, if a research, that should be researcher, consistently sets his or her significance level at 0.01 instead of 0.05, which is typical, will he or she commit more or less type 1 errors? God, alpha is the probability of committing a type 1 error. So if you take this and lower it, then you're going to lower the probability of committing a type 1 error. You're going to commit less of those. If a test of hypothesis is number 10, if a test of hypothesis is conducted when that should be a comma there. I put this together really late one night, and apparently I wasn't all together. Oh well. If a test of hypothesis is conducted when when is the result considered statistically significant? Well, it's when your p-value is less than alpha, or when you reject the null hypothesis. Okay? You might say, well, those are the same things. Sort of true. When your p-value is less than alpha, you reject the null. But we saw earlier in this handout that you can make a decision on the null other ways than using the p-value. You can base it on a confidence interval. You can base it on a critical region. So they're kind of saying the same thing. This leads to this, but this doesn't necessarily lead to that. I mean, they're the same thing, but you may have come up with this decision by not using this technique. So that's all I'm saying there. If that's too heavy for you, then that's cool. You'll be fine. Number 11, a political strategist polled. I looked this up. I think. Yeah, I did. A political strategist polled 1,000 Americans who described themselves as Republicans or Republican leaners. Of the 1,000 polled, 190, which is 19%, said they intended to vote for the Florida governor, Jeb Bush. Later that evening, this is true, based on the results of this poll, CBS reported that 19% of Republicans or Republican leaners intended to vote for Jeb Bush. Is this a correct statement? Discussed. It's not a correct statement. And this is where the media screws up reporting statistics each and every day, hourly, minutely, secondly. They screw it up. What would be appropriate for CBS to have reported is that 19% of those polled intended to vote for Jeb Bush. Now, so what would be better to say? What would be better to say is to take our p hat and create a 95% confidence interval. And we could do that. And they could have done that, which is really kind of goofy. It's not that hard. Tell them to go buy a calculator. Easily done. So we had 190 out of 1,000 that were sampled, and we want a 0.95 level of confidence, so we could calculate. So what would have been much more appropriate to say is that between 16.7% and 21.4% of Americans, well, not Americans, of Republicans or Republican leaners intend to vote for Jeb Bush. So that would, if it does come up where it actually does happen and 21% of Republicans or Republican leaners voted for Jeb Bush, then it doesn't discount the statement, the information from the sample of 19%. It's reasonable because we have margin for error. But 19% is the estimate of P, and the best way to estimate P is to use a confidence interval. And one thing that you can almost be guaranteed is the P hat that you get, the percentage you get from your sample, which in this case is 19%, is never going to equal the population percentage. We just don't get that lucky. Okay, it's just not probabilistically sound to think that. Guys, final handout here. Data is collected on two variables, x and y. If the regression model is y equal 2x plus 4, what is the residual for the ordered pair? 315. Well, just like before, what's a residual? It's the observed y minus the predicted y. So guys, your observed y is right there. It's 15. Your predicted y can be found by putting this x value into our model. And we can just do the mental arithmetic here. Put 3 in here. 3 times 2 is 6. 6 plus 4 is 10. The residual is the difference of these, which is positive 5. The residual is the observed value minus the predicted value. So we would say here that the observed value is 5 units higher than what our model predicted. All right, gang, this is it. You should be very happy. This is the last video of the semester, so it's been real. Hope you haven't gotten too sick of me, but you probably have. That's okay. Take care.